AUTOSAR. Explained by Annette Kempf.
Welcome. Thank you for your time. Today we'll have a look again on AUTOSAR Classic Platform. You see in the navigation autosar.org standards, and it's the standard Classic Platform within the standards here. And in the first session, we had a look at the different parts of the standard and went then into AUTOSAR Classic, having an overview on all the different layers of AUTOSAR Classic. And in the last event, we had a look at the microcontroller abstraction layer, meaning microcontroller and then the abstraction. And today we'll have these green boxes. As you can see, the complex driver has no button to go into to see more details. Complex drivers are used for specific needs. So if you have certain requirements which are not part of the standards, then you might need a complex driver, and the complex driver might need directly to have to access microcontroller resources and will have an interface via the runtime environment to the application layer. So it passes the three layers, or includes the three layers of microcontroller abstraction, ECU abstraction, and also to a certain extent the services layer. Examples for complex drivers are in the older combustion engine world, the injection driver, the ignition driver, the knock driver, which is identifying if here the combustion process did not work according to what you want, and then you get a noise which is knocking. And these drivers are very complex, and they are really very complex. So they are complex drivers needing different resources. So this is an example. But as these complex drivers are highly specific, there is no specification on how it's implemented, like a standard specification. There's only the approach how to deal with complex drivers. For the rest, it's easier. The ECU abstraction layer, there we have I/O hardware abstraction. We have a communication hardware abstraction. We have wireless communication hardware abstraction, crypto hardware abstraction. Maybe also to mention that it's like crypto drivers, crypto hardware abstraction, crypto services. And for memory, it's the same thing: memory drivers, memory hardware abstraction, memory services. And then we have also this onboard device abstraction. So this is the ECU abstraction layer. This means also you can distribute functionality via different ECUs. And this means you are now abstracting the level which ECU it is on. With these services and communication, so it's possible to distribute also functionality via different ECUs. And the I/O pins on the same microcontroller. This is why it's spanning both levels. For each of these boxes, you have a set of specifications behind on a separate page. So if you click, you will end up at this page. And this is possible for all of them. Yeah. For now, I opened the communication hardware abstraction, which you can see here. And there's different specifications inside. I chose the current release. It's the 2311, with all the documents which have been released new with new content update for this release. For example, you have here specification of core test, CAN interface, Ethernet. So you see all the classic communication, LIN, FlexRay, GPT driver, CAN transceiver, and so on. As an example specification, we will have just a short look at the CAN interface, which is opened here. In general, you have the same structure in these documents, and they can be quite long. So in this case, it's 228 pages for the CAN interface from Classic Platform in the current release. You see the document history. It's always like this, showing how often it has been changed, when, and what was the changed content. You always have a disclaimer, and then you get to the table of contents, and you always have the same acronyms, related documentation, constraints and assumptions, dependencies to other modules, requirements tracing, the functional specification, which is a lot here, the interface API specification, which also is quite a lot for CAN, sequence diagrams to understand the flow, yeah, and some other information. What I would like to have a look at in this specification, especially because I like it as a nice picture, so you always get different things, but here it's interesting to see that if you have an external CAN controller, you might go via SPI and not have CAN directly on your microcontroller. And depending on this, you see, if you have a CAN driver, then the communication drivers in the what we saw before, microcontroller abstraction layer is a CAN driver. Otherwise, it's a CAN handler driver. And it's also possible, or you need to handle I/O drivers as well. And then you have this communication hardware abstraction level. Just to have a short look at the specification. And as I said, this specification is quite extensive, and this applies to many of the specification, adding up to a huge amount of documentation. And if you are sitting at a single specification, it's easy to lose the overview. And this is the thing we want to communicate to you today, to have a look again on this level, on the architectural level, on the microcontroller abstraction, not ECU electronic control unit abstraction layer, with all these parts, which is then explained not by me, but by a well-designed e-learning of the Embedded Academy, which is referring to an older version, older release of AUTOSAR, but nevertheless, it's very close to how the standard is defined today, because especially in AUTOSAR Classic, the changes were not that big recently. I hope you enjoy it. We'll now give you a playing in this e-learning, and I will be back soon. Thank you. See you.
The ECU abstraction layer connects the drivers of the microcontroller abstraction layer. It also contains drivers for external devices. The layer is divided into 6 model groups. The onboard device abstraction group contains drivers for ECU onboard devices which cannot be seen as sensors or actuators, like internal or external watchdogs. Those drivers access the ECU onboard devices via the microcontroller abstraction layer. Here you see an example for watchdogs, which uses the internal watchdog driver and the SPI handler driver. The main task of this group is the abstraction from ECU-specific onboard devices. The Memory Hardware Abstraction Group is a group of software modules which abstract from the location of peripheral memory devices, which lie on chip or on board, and the ECU hardware layout. The example shows how internally EEPROM devices and externally EEPROM devices are accessible via the same mechanism, using the internal flash driver, the EEPROM driver and the SPI handler driver. The main task of this group is to provide equal mechanisms to access internal and external memory devices as well as internal and external types of memory hardware. The Crypto Hardware Abstraction Group is a group of software modules which abstract from the location of cryptographic primitives, which can be internal or external hardware, as well as software-based. The example shows how the advanced encryption standard primitive is realized in SHI, or provided as a software library. In this example, the crypto driver and SPI handler driver are used. The main task of this group is to provide equal mechanisms to access internal and software cryptographic devices. The Wireless Communication Hardware Abstraction Group can be seen as part of the Communication Hardware Abstraction Group or as a separate group. The example shows how the wireless communication hardware abstraction interfaces drivers for the off-board communication services. In this example, the involved drivers are the wireless Ethernet driver, the SPI handler driver and the DIO driver. The Communication Hardware Abstraction Group is a group of software modules which abstract from the location of communication controllers and the ECU hardware layout. For all communication systems, a specific communication hardware abstraction is required, for example for LIN, CAN and FlexRay. The communication drivers are accessed via bus-specific interfaces, for example via the CAN interface. Here you see an example for the CAN bus. In this case, the SPI handler driver, the CAN driver and the DIO driver are used. The main task of this group is to provide equal mechanisms to access a bus channel regardless of its location, which can be on chip or on board. The Input-Output Hardware Abstraction Group is a group of software modules which abstract from the location of peripheral input-output devices and the ECU hardware layout, for example microcontroller pin connections and signal level inversions. The example shows how the different input-output devices might be accessed via an input-output signal interface. In this case, the SPI handler driver, ADC driver and DIO driver are used. The main task of this group is to represent input-output signals as they are connected to the ECU hardware. These signals could be, for example, current, voltage or frequency. Furthermore, the layer hides ECU hardware and layout properties from higher software layers. We can see that all groups offer an application interface for access to peripherals and devices regardless of their location and their connection to the microcontroller. The main task of this layer is to make higher software layers independent of the ECU hardware layout.
Welcome back. I hope you enjoyed it. So having now had a look at the ECU abstraction layer, we already covered microcontroller, the microcontroller abstraction layer, the complex drivers, and now the ECU abstraction layer. And there are 3 more layers to come, like the services layer, the runtime environment, and the application layer. So I'm really happy if you join in again. Thank you for today. Bye-bye. Have a nice day.
If you want to learn more about AUTOSAR and other interesting topics, go to embedded-academy.com.